Now let's discuss accelerations. So for acceleration, for the first observer, we're interested in this quantity. And for the second observer, we're interested in the quantity d square x prime, x prime dt square. That is, what is the rate of change of their velocity with respect to time. So this, in other words, can be written as dv prime dt prime. And this dv prime dt prime, again, because t prime is the same as t, this can now be written as dv prime by dt. And because we know the dictionary now, which relates v prime to v prime is simply v minus dA by dt in the more general case. This A refers to the displacement between the two observers, which is different from this acceleration that I've written down over here. So maybe now that displacement I will denote, instead of A, I will use S, okay, over here. Just a small change in notation. So I will use ds bar dt. So that original displacement between these two observers, which I had written as A of t, I'm now going to rewrite that as S of t. This is a change of notation. Okay. And so now, when I look at dv prime dt, this dv prime dt can be written as dv bar minus which can be written as dv dt minus so if I look at this, this is nothing but the acceleration as seen by the first observer. So acceleration measured by the second observer is the same as the acceleration measured by the first observer minus, and this quantity we can write down as A relative, that is relative, this is relative acceleration between observer let's call it S and S prime. No, sorry, let's say observer 1 and 2. Okay. So this is the dictionary that relates acceleration. So we learned a third word now. Okay, the third word of our dictionary, okay, after position, velocity, we've now learned acceleration, and we learned how to translate accelerations between different observers. Again, for the specific case where this displacement vector S, which we had written as A earlier, is v relative times t, a constant vector times t, that is, they're in a state of uniform motion with respect to each other, then d square s dt square is 0. And in this case, the dictionary word for A prime becomes the same as the dictionary word for A. What that means is the acceleration as measured by the second observer is exactly the same as the acceleration as measured by the first observer. Okay. So this is special case of uniform. When we say uniform, we mean motion with constant velocity. Special case of uniform relative motion between the two observers. And when I say acceleration measured by the second observer, this is acceleration of a particle. Okay, this is acceleration of a particle again. Some object that both observers are looking at. And this key thing that does the translation between these two dictionaries is the relative acceleration between the two different observers. Okay, and in the special case of uniform relative motion, that relative acceleration is 0, and the acceleration of any particle as measured by the second observer is exactly the same as the acceleration as measured by the first observer. Okay. Now let us come to Newton's laws and what the implication is for Newton's laws. So for dynamics, if we want to describe the force acting on an object, that force is mass times acceleration. So you have an object sitting over here, a force acts on it, okay? But clearly different observers describe the acceleration differently, as we have seen, okay, at least in the more general case. So for general observers, one observer who's moving possibly in a non-uniform way, that is not with constant velocity with respect to the first observer, they would see, so by applying our dictionary, we'll assume that the force measured by the second observer both observers see the same force acting on the object, so they have this dictionary. But they clearly differ in the definition of acceleration. So let's assume that this is the law that observer 1 learns about by doing experiments. Okay, so they see that if there is a force applied on an object, this object will accelerate with an acceleration a. Okay, and this would be in proportion to the mass of the object. Now we want to see, given the fact that observer 1 measures that under the action of a particular force, the object is accelerating with an acceleration a, what would observer 2 see? We already have the dictionary which tells us what observer 2 measures given measurements that observer 1 measures. So we can just plug in our relationship between a prime and a into this equation. Okay, and what that would tell us is that observer 2 would measure a force F prime, which would be the same as F, but what they would see would be this. Okay, how did I get this? So I just took the original law, F is ma, as measured by the first observer, and I applied the dictionary and I rewrote a in terms of what the second observer should see. That is m times a prime plus ar. Okay, and both observers are measuring the same force on the object. Okay, so this F is F prime. It's the same thing that's exerting a force. Let's say you're pushing on it and it's the same force that both observers are seeing. However, what you see now is that according to the second observer, this law looks like this. Okay, so observer 2 sees this law. And what this says is the force measured by the second observer, okay, produces an acceleration a prime okay? But only when I take into account an additional pseudo force which arises just from the fact that the second observer is accelerating with respect to the first observer. So let's come to a physical example of this. Again, suppose you are standing on the ground and you have a friend in a car, and she's driving to the right, but this time she doesn't just have a uniform velocity with respect to you, she actually has an acceleration, AR, relative to you. This is her relative acceleration. And now imagine that as she accelerates, okay, you ask what she would see, and what she experiences are pseudo forces. Okay, that is, she experiences a force which is minus m times AR. This is the pseudo force that she experiences. Okay, and this is just due to the fact that her car is accelerating to the right, and as she accelerates, objects in the car would appear to have an which are let's say not acted on by anything. For example, you imagine that there's a balloon floating around in this car. It would appear to her to be accelerating to the right with an acceleration AR. Okay, in reality, the balloon is at the same place and she is accelerating to the right. And so the balloon appears to be accelerating backwards because of her acceleration in the forwards direction. Now, she can attribute no physical cause to this. There's nothing in contact with the balloon. She would simply say that there is an extra pseudo force that appears out of nowhere. Okay. Now, this is true for any observer who's accelerating with respect to the original observer for whom Newton's laws appear to be valid. So we can separate out classes of observers. Okay, these are there are what we call inertial observers. These inertial observers see that Newton's laws are valid for them. And there are so-called non-inertial observers who see Newton's laws are not valid, and they need to take into account pseudo forces. Okay, so the law F is equal to ma is valid for these observers. So if you take this special case where AR is 0, okay, in those special cases, the force F prime, as seen by the observer 2, which is the same as the force F, okay, which is a force which can be attributed to a known cause, like someone pushing on the object, would result in an acceleration that is directly proportional to the force divided by the mass of the object. Okay. So the same law is valid for observer 2 as it is for observer 1. That is, observer 2 would see F prime is ma prime. The force, I have to use a dictionary, and we say that the force is the same. And the acceleration, I apply my dictionary and find the new acceleration, and I find that when I apply the dictionary, Newton's laws are valid for the second observer and for the first observer. Okay, so inertial observers are those observers for whom Newton's laws are valid, and therefore these observers all have constant relative velocity with respect to each other. And that means that they have no acceleration with respect to each other.